Welcome again. In this video we will solve time-independent Schrodinger wave equation for a special potential energy function, that is delta function potential. And we will solve this Schrodinger wave equation for systems where total energy is greater than 0, and such systems give rise to scattering state. What is scattering state is already discussed in the previous video, link of which is given in the description below. In the previous video I discussed the bound state where total energy is less than equals 0. To remind you again, a graph of the potential function is given here. This is like a potential wave. The function can be given as del x is delta function is denoted by this del x notation, and is equals to infinity when x equals 0 and is equals 0 for x not equals 0, and the integration of delta function from minus infinity to plus infinity equals 1. All the theoretical base has been given in the previous video, so you can refer to the previous video. In this video we will directly solve the Schrodinger wave equation, the time dependent Schrodinger wave equation. First let us write the Schrodinger wave equation. So this is the time independent Schrodinger wave equation. Psi of x is the eigenfunction and v of x is the delta function, the definition of which I have already given. So let us solve the Schrodinger wave equation, and we can separate the region in two different region for x less than 0 and for x greater than 0. So like in reality, from the description of the delta function, this width is actually tends to 0, so we can just neglect this region for now, and the definition of delta function will come in the discontinuity of the first derivative of should be the first derivative of psi of x. So for this you can again refer to the previous video, and we will again see how the discontinuity of the first derivative of psi of x affects the solution. So first of all, let us solve it for x less than 0. You can see that for x not equals 0, fx, that is the vx, the potential function, is 0. So Schrodinger equation reduces to, we can write it as minus of 2me h bar square psi of x. Here we can introduce a new variable, that is k, and k is equal to 2me h bar, and here k is greater than 0, so k is a positive quantity, k is a real quantity. So now we will directly write down the solution of this differential equation, that is equal to a to the power I kx b to the power I e to the power minus I kx. So there is some standard procedure for solving this differential equation. I won't discuss them in this video. You can refer to some books like SCOM series differential equation book, and for now, if you doubt whether this is a solution to this differential equation or not, you can substitute the psi of x in this equation, and you can see that it satisfies this differential equation. And for this is a second order differential equation, so there are two unknown quantities, and physically this term denotes a wave traveling in the plus x direction, and this denotes a wave traveling in the minus x direction. Now let us solve the Schrodinger wave equation for x greater than 0, and again the Schrodinger wave equation will reduce to this one, that is square twice m x square psi of x e into psi of x. The solution will be same as this one, but the unknown quantities will be different here. So psi of x should be written as this c e to the power I k x plus d e to the power minus I k x. And here, like in the previous video, you can see that psi of x was something like e to the power I k x, and b solution was minus kx. In this case, when x goes to plus infinity, this term had blown up, and for x going to minus infinity, this function had blown up. But in this case, this is the argument of exponential function is a imaginary term. There is an iota term, so it won't blow up whether x goes to infinity or minus infinity. So we cannot neglect any of the term. Here also we cannot neglect any of the term on the basis of the infiniteness of the eigenfunction. So to remind you that eigenfunction should be single valued, and these two eigenfunctions are single valued, and it should be finite everywhere. So even if x goes to positive infinity or negative infinity, psi of x is finite in both the cases. But if you imagine both the eigenfunctions physically, you will find some inconsistency in the coefficient. So for there is a delta function, well, at x equals 0, this is x equals 0. So for this eigenfunction, there is a wave traveling in the positive x direction, and there is a wave traveling in the negative x direction. So some wave is coming from the left, there may be some source, so it strikes the potential well, or it may be reflected, or it may be transmitted. Whether it reflects or transmit, we will see it in short. So there should be a wave in the positive x direction here in this region, and there should be a wave in this negative direction in this region. So both the terms in these eigenfunctions is physically acceptable in this argument. But in here, in this case, there is a wave traveling in the plus x direction. Okay, there is already a wave traveling in the plus x direction, but there is again a wave traveling in the minus x directions also. But there is no potential barrier, nor no potential well, or no source in the extreme right, so there shouldn't be any wave traveling in the negative x direction in this region. So d must be equals to 0. So the final eigenfunctions are, so the eigenfunction should be this one for x less than 0, and for x greater than 0 eigenfunction is this one. Now we will have to apply the boundary conditions here. The first boundary condition is that psi of x should be continuous everywhere, so it should be continuous at x equals 0 to, so it will give rise to putting x equals 0 in this eigenfunction and x equals 0 in this eigenfunction, we will get a plus b equals c. And for normally first derivative of psi of x is continuous everywhere too, but in case of delta function, as we have already derived in the previous video, again you can refer to the previous video, a link of which is in the description below. We had derived that discontinuity of the first derivative of psi of x is equal to minus of 2m alpha divided by s square the value of eigenfunction at x equals 0, and this alpha is a positive quantity, alpha greater than 0, and this is in the description of delta function actually. And the potential was in this case minus of alpha into delta function. Originally delta function goes to positive infinity at x equals 0. For this definition, for delta x minus a, it goes to infinity at x equals a, and when we multiply it by some positive quantity, some negative quantity of a negative quantity, there creates a delta function well in this case. So it goes to negative infinity at x equals a in this case, or x equals 0 in this case, or x equals a in this definition. So now writing the first derivative of x for in the right hand side derivative. Okay, right hand side derivative is in this case from this ci of k e to the power I k x, and right hand side derivative add x equals, and add x equals 0, it will be ci k, and left hand side derivative will be minus, will be from this side of x we will get a I k e to the power I k x minus b I k e to the power I k x. So change in the first derivative will be equal to so I k term will be common, c minus a plus b. Now putting a plus b equals c, so now let's write b equals c minus a. It will be twice term will be here, c minus a. So this term is equals to minus of 2m alpha h bar square. The value of the eigenfunction at x equals 0 will be c if we put x equals 0 or a plus b, but in this case x plus b, a plus b equals c, so you can write c here. Psi of 0, okay, psi of 0 is c here, 2 cancels out, so the finally we get iota k c minus a, and minus of m alpha is per square, c is here. Now let's solve for a in terms of c. So in terms of c is this formula. Again a plus b was equals to c, so writing b in terms of c will give, okay, b in terms of c is this one, but there is still a unknown quantity remains, that is c. In general case you should have been come from normalizing the wave function, but in this case as it represents a free particle, so like if you write down the wave function time dependent, so what where we're solving is psi of x, if we multiply it by time function we get the real Schrodinger wave function, so that is equals to a e to the power I k x plus b to the power I k x. We had got these terms there, and if you multiply it by I e t by its bar square we get the wave function. So it represents a free particle, and free particles are not normalizable. To get it to be normalizable we can we can write it as the linear combination of all the possible states. So we will discuss it in short, but before that we would like to see some physical mm, significance of our results. So first of all we would like to derive the reflection coefficient at the delta function valve. In classical wave, reflection coefficient would have been simply just the ratio of the reflected amplitude of the reflected wave, that is v, and the incident wave, and b was this in this case and a was this, like a was the reflect incident amplitude of the incident wave, as this represent the wave traveling in the plus x direction, and b per minus I k x represented the wave going in the minus x direction. But in quantum mechanics the reflection coefficient doesn't depend just on the ratio of the amplitude, it depends on the intensities. Intensity comes from b star b, it is the complex conjugate of b. So what it actually represents, it represents the probability density function. In quantum mechanics probability density is the only physically realizable state of a wave function. Probability density represents the probability of finding a particle at some distance dx. So refraction coefficient depends on the probability of finding a particle to be represented by a wave coming in the minus x direction, that is the reflected wave, and sorry, this should be brackets only, and to the ratio of the probability of the incident wave. So we can write the value of b star and b from this. C into minus of I, complex conjugate of b is a k h bar square. Now c I m a k h bar square, and there will be a complex conjugate of a will be plus of I m a k h bar square, and a was minus I m alpha, sorry, it was alpha k h bar square, and it will give, sorry, it was, there was c, and it will give and writing k in terms of e, k was just equals to 2m divided by its bar square. We will get reflection coefficient to be equals to, and dividing, like making here unity, we will get plus 2 h bar square e and by m alpha, so m alpha square. Okay, this doesn't mean any square term. Again we can derive the transmission coefficient. The probability of a incident wave to be transmitted is the intensity or the probability density of the transmitted wave to the incident wave, and we can derive it to be like following the same standard procedure. We will get 1 plus m alpha square 2 h bar square e. So we can see that, and if you add r plus t, you will get 1, and it simply means that the incident wave will be either transmitted or reflected. So probability of transmission and reflection is equals to infinity, and it is simply just obvious. And you can see that when the energy keeps on, probability of transmission will be increasing, and if it keep on decreasing, the probability of reflection will be, the probability of reflection will be higher. Okay, it just simply you can just see that the barrier is something like, sorry, this is the delta function potential. If the particle has some enough energy, it will be transmitted. If it doesn't have some enough energy, it will be reflected back. As the derived wave functions are not eigenfunctions, it was were not physically realizable, and it was not normalizable. We will look at what is the real physical significance of the derived wave functions, and like first look at the wave function of a free particle, as it was also not physically realizable. We will look at this problem in details in some other video, but let us summarize it here. So it is the wave function of a free particle, and it is also not physically realizable. But in like as you know, the wave function is the linear combination of, it is linear in psi of x. Schrodinger equation is linear in psi of x or psi of xt, as the general solution is the linear combination of all the wave functions, like there is a subscript n and multiplied by some coefficient c of n. So here actually this wave function is valid for some energy E of n, so you can write it as E of n, and the general solution is psi of xt is equals to the linear combination all the psi of n xt. And like for free particles where it is not normalizable, this summation transforms into integration. So here you can write it psi of xt as this terms comes from symmetry. You will get to know about it from if you study Fourier analysis. So it is from minus infinity to plus infinity, and this coefficient is a function of k, and e to the power I k of x minus e by h bar t and d of k. And how will we solve phi of k? And it comes from the Fourier analysis. Let the wave function be this one at x t equals 0, so it will be reduces to phi of k e to the power I of k of x from d of k. And from the principles of Fourier analysis, k will be simply this there will be a minus term, and this will be integration will be with respect to x here instead of k in the previous equation. So in this case we can calculate the phi of x, the coefficients. In the same way, for the present problem we can solve the coefficient of the wave functions, so that we can get a general solution, and general solution is physically realizable and it is physically acceptable. So this is all for the delta function potential, and we have discussed the Schrodinger wave solution of the Schrodinger wave equation for delta function well, for both for bound state, and in this video we studied it for scattering state. Thank you for watching, and you can refer to the previous video in the descriptions below.